Okay, so Boltzmann equation is very important to understand the number of particles, to know more about the number of particles in a given energy state. Okay, it is just like your radioactive decay equation which you have studied up to into the 12th side. Okay, so the same way we can write the number of particles using this Boltzmann equation. So if you look at the formula, that is very simple. I have highlighted it also. So which is n equal to n naught e to the power minus capital E upon small k capital T. Okay, so these alphabets are really very important, because the moment you change it capital K or capital small e or something, everything is going to be changed the meaning. So you look at this n equal to n naught e to the power minus e, which is capital E upon small k into t. Now let me clarify you what is the exact meaning of each component. N is the number of particle. Okay, n naught is again number of particles, but in a certain state, in the, let's say, in the ground state. Okay, we'll discuss more about in these details. And then e to the power minus e, this e capital E is the energy of that level. Okay, and upon k is the Boltzmann constant, and capital T is the temperature. Okay, so these are the things we are used in the formula. And now you see about this formula is useful to define the number of particles in a level, in energy level. And if you remember from the last lecture, that we have discussed that whenever we talk about the atomic system, that means there has to be at least two energy levels. Okay, or it can be more than two also, but only one level is there, then we are not considering as a system. Okay, so right now I'm talking about a, let's say, system. So there has to be two energy levels. This is the general form to find out the number of particles in any level. So let's say the general formula is n equal to n naught e to the power minus capital E upon kt. Now if you look at closely, then you see how the particles or the atoms are arranged in different energy levels. So by general, you already know that most number of particles are trying to stay in the lowest possible state. That means minimum energy level state, because they don't want to move to the higher excited state by its own. So general tendency is they want to prefer to stay at the lowest possible energy states. Okay, the other thing is, which I mentioned in the serial number 2, that number of particles in each energy level decreases with the increase of energy level. I think we have put one diagram also in the earlier slides, if you people have noticed properly. So that if you go to the higher energy level, fine, the energy will be large, and in that case the number of particles are getting less and less. And that's why we are saying, if I consider the ideal case, in that ideal case, let's say maximum number of particles will be in the ground state because it has minimum energy, and very less particle will be in the upper state because it has very high energy. So almost, if I say ideal case, so infinite number of particle has to be there in the ground level, and almost zero or few particles may be there in the upper level. Okay, excited level. And you people are knowing already that excited level is, I mean, to maintain or to stay in the excited level is very difficult. So that's why mostly the particles belong to the lower level compared to the higher level. So that's why I have written these two statement, that as soon as you go to the higher level, the number of particles are getting less and less. Okay, so just keep in mind this particular equation, because we are going to use this various times. Okay, so I'm going to the next, relative. Okay, so as I said, I am talking about a atomic system, an atomic system where at least two energy levels has to be there. So let's consider that there are two energy levels. Okay, and the energy of each level, let me define. Let's say if the energy level, if it is energy level 1, then the energy is E1. For energy level 2, the energy is E2. Okay, or you can simply call it as a energy for ground level, energy for upper level, but it is always preferable that you write level 1 and level 2, because when you go to the a more energy level system, that means 2 level, 3 level, 4 level, something, so it is always preferable you write the proper naming. Okay, so first energy level, second energy level, like that. So here the energy level is having one first energy level, let's say E1, energy is E1. Second energy level, the energy is E2. And now if you write the number of particles in each level, okay, so don't confuse with the word energy states or energy level, both are same. Okay, so if you define the number of particles in each energy states, or let's say in the energy level, okay, so you just use the same Boltzmann equation, that is n equal to n naught e to the power minus k by t. So you have to replace the terms, that's it, because if you are talking about the number of particles in, let's say, level 1, so simply you have to write on the left hand side n1. Okay, this n naught is the total number of particle. Okay, so just keep in mind, if you look at again into the earlier slide, this n is the number of particle in any particular state. Okay, n naught is the total number of particle which is present in the system. Okay, so now actually we are coming in more deep depth. So n1 is the number of particles in level 1. Okay, n naught is the total number of particle present in the system. It is not in the level, it is present in the system I am talking. E1 is the energy of level 1. Kt is the, of course, constant. Now again you see, for level 2, n2 equal to n naught e to the power minus e2 by kt, right? Again, n naught is the total number of particles present in the system, n2 is the number of particles in the second level, e2 is the energy of second level, and k and t is there. Okay, so I hope this is clear. Let me highlight it also if you want, so you look at here. This one is the highlighted part where you see n2, how we are defining. Same way, see, these numbers are having no meaning until you get a relative number. Okay, so that's why what people are doing is they are finding the relative number, let's say n1 by n2, or if you want, you can find out n2 by n1 also. There is no harm in that. So it is completely your choice which one you want to prefer. So I prefer n1 by n2. So I have taken out the ratio of n1 by n2. You divide it, this n0 will cancel it out, of course. And if you rearrange the terms little bit, so you will be getting a term will be this one, e to the power e2 minus e1 by kt. I hope this is very simple mathematics and you people are able to do that. And now if you remember carefully this e2 minus e1, let's go to the again same thing. What is e2? E2 is the energy level, e2 is the energy of level 2, e1 is the energy of level 1. And here it is the difference of these two, e2 minus e1. Now if you remember carefully, in the earlier lecture we have discussed that whatever the amount of energy you provide to the lower level particles, lower level state, okay, and it is, if it is absorbing the energy, it will reach to the upper state. Okay, so that energy is nothing but the energy which you have supplied from the outer source is nothing but the energy level difference between level 1 and level 2. So this E2 minus E1 is nothing but the amount of energy which you are supplying from the external source. And if you remember carefully, that amount of energy we have denoted with the h nu. Okay. And again, if you remember, I have told you this h nu is not only for a particular light. Okay. It depends on the frequency of the source. So that is why whenever we talk about h nu, yes, delta E, some people are calling it as delta E also. Either you can call it delta E or you can simply write it in terms of h nu. Okay, but important thing over here is this h nu is not only about the, see, whenever you see h nu or something, we are saying it's a photon. And whenever you talk about photon, you people are thinking, okay, it is going to be the light photon only, nothing else. But forget about that. Whenever we talk about h nu, that means that can be of light photon also. I mean, it depends to the light also, or it can be infrared photon also, it can be microwave photon also, it can be UV photon also. Okay, provided it depends on the frequency nu. Okay, so delta E is nothing but basically h nu only. Okay, so don't specify, always write h nu only, because h nu depends on the source frequency. If frequency is changing, then of course your h nu value is going to be changed. Okay, and upon kt. So this particular result you can note it down if you want in your notebook. So n1 by n2 is nothing but e to the power h nu upon kt. Okay, we need to discuss again, like, what is the meaning of n1 by n2? We have taken out the relative numbers. Okay, we have find out n1 by n2, or you may find out n2 by n1 also. But what is the meaning of finding it out? Okay, what is the purpose of n1 by n2 or n2 by n1? So let's look at it out. It provides many details. Okay, so look at this particular ratio n1 by n2 depends on which parameter. Okay, again let me go to the previous slide. Okay, now you see this one, this n1 by n2, and this one. Okay, left hand side and on this right hand side. Now can you see on which parameter it is depending? So one is this h nu, that is the energy of the system, and the other one is, see, k is the Boltzmann constant, that is constant only, nothing else. You cannot deal with
Temperature.
that. The other thing is the temperature. Okay, so it is written over here also. But if you again see carefully, at lower temperature, most number of atoms or particles are there in the ground state. At higher, if you increase the temperature, of course atom will move to the higher state, right? So this n1 by n2 provides you the details. Again, if you see more carefully, so this one also, at thermal equilibrium, more a number of atoms. Whenever I say thermal equilibrium, means the room temperature I am talking about. Okay, so generally not room temperature, but you say when the temperature is set between a system, it is not fluctuating much, it is equilibrium case. So in that case, you see more number of atoms will be there in the ground state compared to the excited state. Okay, because it is the case of equilibrium. But if you are increasing the temperature further, then of course it is going to the higher state. Now other thing is, you see, the number of excited atoms can be large if the energy level is very close. So there are two probabilities. Either if you want to increase the number of atoms in the higher state, then either you keep the energy level very close, or you make the temperature very high. Okay, so if you are keeping the temperature very high, of course people, I mean participants are, sorry, particles are getting energy, or atoms are getting energy, and they are reaching to the higher state. Fine. So these are the two way by which you can increase the number of particles or atoms in the excited state. Now let's see some limiting case. Okay. Now what happens if this energy difference E2 minus E1 is 0? That means both the energy levels are almost at the same point. Okay. The difference is almost 0. Then what may happen in that case? If you put this result into the previous formula, then it comes out to be like N1 equal to N2. That means if there is no energy level difference between the particles, between the levels, then the number of particles in each level are equal. That is n1 equal to n2. Okay. Other limiting case, suppose if you increase the temperature further and further, and let's say you make it maximum. Okay. So you see the second limiting case. That means if you make t as infinite, then again your number of particles are going to be equal. So are you getting any idea what
Sir,
does exactly mean?
sir, uh,
Yes, yes.
uh, I'm not clearly able to understand the second limiting case, that is t is infinite. Like from equation, I'm understanding that n1 by n2 will be 1, but
Yes.
like I'm not getting the feel of it. Like there will be photons in n1 also and n2 also.
Yeah, okay. Let me clear it out. Okay. See, the purpose over here is to find out this activity n1 by n2 is we need to see to generate the laser light. Okay. The important thing is we need to go for the stimulated process. All right, as I discussed in the earlier side. Now, to increase the number of stimulated process, what we required is the number of atoms in the upper state has to be maximum. Okay, let's look at into this manner. There are already particles which are there in the ground state. Okay, but to generate laser light, what is the requirement? What we required is the number of particles in the upper level has to be more and more compared to the lower level. So let me put it again in two cases. One is the general case where the number of particles are more in the ground level, very less in the higher level. But in that case, laser will not emit. To emit the laser light or to generate the laser light, the requirement is upper level must have maximum number of particles and lower level must have minimum number of particles. That means the completely reverse process, completely inverse case. Okay, and that is why later on we'll discuss about it also. That term we are saying is a population inversion. Okay, so normally the population is maximum in lower level, minimum in the higher level, but if you just inverse it, that process we are saying is a population inversion, in which maximum number of particles are in the upper level and minimum will be in the lower level. And to generate the laser light, this is the requirement. Okay, why we are discussing about this, let me clear it out. Because we want to see whether are we able to generate more number of particles, are we able to process more number of particles at higher level or no. Okay, so those who are new, let me tell you that n1 is the number of particles in level 1, n2 is the number of particle in level 2. Okay, so n1 and n2. So if there are only two energy levels, right, and you want to generate laser light with two energy level system, requirement is one, it has to be the follow the stimulated process, emission process, and the second is number of particles has to be maximum in the upper level and minimum in the lower level. But in two level system, the problem is, even though if you are increasing the temperature, as I said earlier, how number of particles are going to increase in the upper level? When you increase the temperature, or either you are putting the energy levels very close to each other. So I have considered both the case. If I keep both the levels very near, let's say almost tends to 0, then also you see what happens, number of particles are going to equal. In any case, number of particles in the higher level is not going to exceed with the lower level particle. The maximum thing you can see it is getting equal. Are you getting the point idea? In normal case, n1 is always larger than n2. Okay, in normal case, at normal room temperature, n1, any number of particle in level 1, it is always larger compared to upper level particle n2. But if you keep these cases, let's say energy level difference is almost 0, then also you are not able to make n2 larger than n1. The possible case will be n1 equal to n2, but our requirement is n2 has to be greater than n1. So that is
Hmm.
not possible even though you keep the energy level difference almost equal. Okay, then I consider the second limiting case. Let's say if I make it temperature very large, let's say if I go to the infinite side maximum, then also you see at a particular time the number of particles can be equal with each other, but you cannot make n2 larger than n1 in any case.
Sir, that is where I'm confused. Like, if the temperature is very high, then most of the photons, like all of the photons, should be in N2.
No, but in two level it is not possible. Now you see the this formula, because it is only two level system. If you are talking about three level or four level system, then the case will be different, right? But right now only two levels are present. Okay, and they must follow this rule. Okay, this Boltzmann equation form they need to follow. N naught is the total number of particle, okay, present in the system, right? So
Hmm.
n1, if it is maximum, then n2 will be less, fine, or n2 will be more, n1 will be less, or both are equal. So you see, out of three cases only two are going to be possible with this form. If you see on the screen, okay,
Yes, sir.
with this formula only two possible cases are possible. N2 cannot be larger with n1 in two level system using this formula.
Hmm.
Are you getting that? You can provide the result. As I told you, this factor is depending only on two parameters. One is the energy level difference, which you see on the screen. Here it is. And the other is this temperature. So in the next slide, I have considered both. I have applied both the cases, and in both the cases, I find out that the maximum thing which I can achieve in two level system is the particles can be equal in each level.
Right. Okay, thank you, sir.
Are you getting that point?
Sir.
Again, I'm repeating, my purpose is, if I need to generate a laser light, the number of particles in the upper level has to be maximum, okay, and minimum into the lower level. But that is not possible in the two level system. Even though if I increase the temperature as high as possible, even though I keep the energy level difference as minimum as possible, in both the cases the particles can be equal, it cannot be more than in the upper level. Is it
Right,
clear?
sir.
Right,
Yes, sir.
we'll discuss, don't need to worry. Again, when we apply this particular formula, that time it is more clear to you people. Okay, so again, that references I used to give. Okay, now coming to this, the
Sir,
important. Yes, yes.
here thermal equilibrium is room temperature only.
Yeah, yes, whenever you talk about the thermal equilibrium, means a temperature where there is a equilibrium in the in the system. So you see more clear, specifically we have used in this slide. So this equilibrium basically is like, see, thermal equilibrium you cannot say at room temperature always. Okay, it is a equilibrium where two systems are matching at the same temperature. Okay, so if the temperature is same for both the system, then only we are saying as a thermal equilibrium. It is not always room temperature,
Yes, sir, got it.
right? Thermal, because temperature thing is there, so we are using the word thermal. But equilibrium in the sense whenever the temperature is same in both the system, that time we can say is thermal equilibrium part. It is not room temperature. So keep in mind that. Okay, so here again you see Einstein's A and B coefficient. Okay, because this is again the base of laser physics, and we need to find out a relation between A and B. Okay, and now what is A and B? So basically these are the constant he considered, coefficient he considered, not constant but it's a coefficient. And if you look at A and B, A is used for spontaneous process, okay, and B is used for the stimulated process. Now if you remember carefully, spontaneous is only one process in which only emission can possible. Stimulated is there are two processes, either it can absorb it, that is also one stimulated process, or it is going to emit it, emission, that also is going to be the stimulated. So spontaneous process is only one, and for that we are referring with capital A. Stimulated processes are two, for that we are going to use capital B. So these are the two coefficients we are using to derive a formula, and we need to find out the relation between
Sir,
A and B. Yes.
can you please give a glance of these two, because I had not attended the previous lecture. No, that is the reason I am not able to understand what you are speaking.
Okay, no need to worry. Fine. So what I'm saying is, as I have shown you earlier, that there are three processes which we are following. है ना? How these electromagnetic components are interacting with the material. First process is the stimulated absorption process. Second is the spontaneous emission process, and the third is the stimulated emission process. So whenever we are talking about, see, that is the main process which is the whole of this laser physics. Now we need to implement these process in a particular system. Okay, so that's why here we are going to apply all these three process. Okay, and we need to derive some conclusion. So that's why we are considering that whenever we talk about the spontaneous emission process, we are going to write capital A to denote that process. Okay, and basically it's the coefficient of this process, and the coefficient for the stimulated process is capital B, right? So A and B we are going to use for different process. Okay, let me give you the idea one more time in the next slide. Okay, so those who are new or missing something, again they can see the final thing is we need to write down, we need to find out the value of A and B, and also we need to write the factors which are affecting this particular process. Okay, so one by one all the three process you need to write down for a two level system. Okay, so we have just discussing about two level system only. Let's talk about the first process, that is the stimulated absorption process. And you look at this process is depending on which parameter. If you, those who have attended the lecture earlier, they can easily identify that this particular process is depending on the number of particles. Okay, and the second thing is the energy which we are supplying from the external source. Okay, and since energy we are writing in terms of energy density, because energy per unit volume, so we are writing as energy density, and energy density is generally depending on the frequency of the applied source. So that's why this U, and in bracket we are writing nu, so that depends that energy density is a function of frequency, right? So there are two parameters on which this first process is depending. If you people are not able to understand, I know it may be difficult for you people at this moment, so let me go through the again the earlier slide. Yeah, now look at, this is the first process. Okay, let me clear it out. Here the number of particles you can see in this part. I hope you are able to see this. In this part the number of particles are maximum in the ground level, very few, one or two maybe in the upper level, right? Now what happens when you supply this amount of energy, h nu, one of the atom will absorb this energy and reach to the upper level there. So you see the color I have changed, it's a black color now. Okay, and here if you look at the total number of particles, in the first diagram it is 9 and 1, in the second it is 8 and 2, but total will be 10 always. At any moment you consider, total number will be 10 only. So if you look at the process, then you just find out this process is depending on which parameter. So first it is depending on the number of particle, but for which level number of particles are depending. So you see the level 1 particles are participating in this process. because from level 1, one particular atom is getting energy and reaching to the upper level. So level 1 particles or atoms are involved in the first process. Apart from that, this amount of energy h nu, that is also involved over here. So basically this process is depend on two factor. One is number of particles or atoms in the ground level, yani level 1, and other is the energy which you are supplying from the external source h nu. Okay, so this energy we are writing in terms of energy per unit volume, and energy per unit volume is nothing but the energy density. So that's why we have, we have written this as a n1 is the number of particles in lower level, u nu is the energy density which you have applied from the external source. Okay, and if you remove this proportionality constant which is there, okay, you get a equal sign, and you need to write a constant over there. Okay, and since I told you that whenever you see stimulated process, you need to consider the coefficient as b. Whenever you see the spontaneous process, you need to consider the coefficient as a. So since it is the stimulated process, so once you remove this sign, this one, okay, this equal sign will be there, and this constant I have used over here, b. Now important thing is, since there are two stimulated process, absorbing as well as emission, so to identify which is the absorbing process, which is the emission process, we are writing this 1 and 2. So if you look at here, 1 2 means process is starting from 1 ending at 2. Okay, so that is why 1 2 we have written b1 2. In case of emission process, we will write 2 1, because starting process from the level 2 and ending at level 1. So v21 we will write in the next process. But here it is the absorbing process, stimulated also. So b, and level 1 से 2 में हो रहा है, that's why we are writing 1 2. Now again let me clarify where n1 is number of particles in ground level, b12 is the proportionality coefficient basically for absorbing process, and u is the energy density. It is not per frequency, but it is per unit volume as a function of frequency basically, noting in the bracket. Clear है ये? Is this clear?
Yes.
Yes, sir.
If there is
Yes,
any
yes,
doubt, then simply you consider all the three process. You just note it down on your notebook and think it properly. Like this process is depending on which factor. Okay, second process is depending on which factor. Third process is depending on which factor. Okay.
Sir, can
Now,
we repeat these all three procedure with that photoelectric part? In there also we does the same thing, no? Giving energy
yes,
and emitting a photon right from that surface.
yes. I mean, what exactly you want? I didn't get it.
I'm asking that can we relate this stimulated absorption and emission procedure to photoelectric effect? The same thing we do, no? There also.
Yeah. You can. Okay. Coming to the next one, the next process, that is the spontaneous. Okay. Now here again you see spontaneous emission process depends only on one factor. Okay, that is number of particles. And one, let me go to the earlier slide. Here it is, right? So in the first diagram, we have already considered the case where the particle is already excited because of the first process. Okay, this dot will be there that represents the atom in the excited state. Now if whatever they are in the excited state, it cannot be there for a longer time. It has to decay to the lower level. If that excited particle decays by its own automatically, so then this process we are knowing as a spontaneous emission process. Okay, so whenever it emits to the ground, I mean whenever it come down from level to the level 1, it will emit a photon. I mean almost same amount of energy it will emit, which is absorbed by this photon, this atom, right? So that amount of photon is going to be emitted again, that is h nu. Okay, so this process if happening by its own, we are calling it as a spontaneous emission process. So now if you look at carefully, okay, and then you find out this process is depending only on the one particular factor, that is the number of particle. But which level? Level 1 or level 2? It is only level 2, because level 1 is having no role over here. Level 2 only, because level 2 is going to be changed. You can see from the diagram, from both the diagram, it is clear. So level 2 particle is getting down to the level 1, emitting some energy. So basically number of particles of level 2 is involving in this process. Another thing you see, is there any energy which I supplied from the external source?
No.
Nothing. Yes, so that is why this particular process, if you look at carefully again, is depending only on the factor n2. Okay, nothing else. So again, if you remove this constant, this proportionality sign, you will get a equal sign and you will get a coefficient. And since it is the spontaneous process, so we are writing as A, capital A. Okay, so either it's a single process, so either you write capital A, or you can write just to identify from which level to which level this process is happening. So it is happening from 2 to 1. So I have denoted 2 1. So there is nothing wrong in that case if you denote with 2 1 also. Okay, so either you write simply A because it is only 1, or if you want to know, define properly, then you write A 2 1. That indicates that this process is happening from level 2 to level 1. That is A 2 1, and N2 is already there. Again, let me clarify, where N2 is number of particles in the excited level, A21 is the proportionality coefficient for spontaneous emission process. Right? Now come to the third process. Okay, stimulated emission part. And this process also depends on two factor. To check it out whether it depends on only one factor or two factor, let me go again to the back side. Here this was the process. In the first diagram you see already the particle is there in the excited state because of the first process. Okay, now it is the time of decay to this, but this time this particle is not going to the ground state by its own. Basically you are forcing this one to go down to the lower level. Okay, and how we are forcing? Via supplying some amount of energy. Okay, the same amount of energy which you have given at the beginning, same amount of energy you need to supply so that the excited particle can come down to the lower level. Okay, so you see that if you look at the process carefully, so this process again depends on two factor. One, the number of particle. Two, the amount of energy which we have supplied from the external source. Okay, but important thing is which level particles are participating in this process. It is only to the level 2 particles, right? Level 1 is nothing is going to be changed. Only level 2 particle is coming down to the lower level. So this process depends on N2 and energy density.
Sir, I wanted more clarity on stimulated emission part. Like we
Yes.
are supplying energy, right?
Yes.
So should it not be like a photon or a particle from ground state comes to the higher level energy state?
Yeah, possible. It is possible.
Then like
You have
if we
joined
are providing
recently.
energy, if we are providing energy, then why is it getting down to a lower state?
No, your question is everything is correct, right? And even I have discussed this thing in the first lecture also. So I will suggest you to just go through the first to second lecture, and we have covered the entire detail, right? What is happening,
Yes,
why
sir.
it is happening with the first level only or two level only. So I will suggest you, those who are new, they at least can go through the first and second lecture. Okay, and
Okay, sir.
your doubts will be clear. I mean, everything will be clear with your mind. Whatever the doubts you may be having, it is all already will be solved. Okay, still if
Okay,
you are
sir.
having doubt after going through the lecture, then we will discuss it again, no problem, right?
Okay, sir.
Okay, so this process is again depending on two factor. N2, that is the number of particles, and energy density. Okay, and again if you remove this sign, you will get an equal sign and coefficient. That is, it is a stimulated process, so we have to write capital B, but this process is happening 2 to 1. Okay, so that's why we are writing as B21. N2 and energy density, where N2 is the number of particles in excited level. B21 is again the coefficient for stimulated emission process, and U nu is the energy density. It is per unit volume, okay, and function of energy. So this you have to keep in mind. Fine. There are a lot of